All right, let's unpack this. Today, we are diving into one of the most, I think, one of the most elegant concepts in all of physics.
Absolutely. Whether you're talking quantum or classical.
Yeah, this idea that the reliability of the universe, the reason things like energy and momentum don't just sort of disappear,
Right.
it's all rooted in symmetry.
Exactly. This whole deep dive is about that beautiful essential link. You take a physical system, you perform some transformation on it,
Like flipping it in a mirror.
like flipping it in a mirror, and if it looks the same, that symmetry directly creates a conservation law.
Hmm.
We all take energy conservation for granted, but quantum mechanics tells us why it's there.
And the reason is the shape of space and time itself. So our mission today is to walk through the logic from the source material, step by step.
Right. How the quantum definition of symmetry mathematically forces these conservation theorems into existence.
To do that, we have to start with the simplest possible example. Feynman calls it the ammonia molecule of the chapter.
The hydrogen molecular ion. It's perfect for visualizing this.
So what is it? Just two protons and one electron.
That's it. Two protons, let's call them 1 and 2, and a single electron that's sort of shared between them. We could define two, primary states for that electron.
Okay.
State 1, written as ket 1, is when the electron is mostly hanging around proton 1. And state 2, ket 2, is when it's near proton 2.
Now, if we assume the system is perfectly symmetric, the protons are identical, the space between them is fixed, there has to be something we can do to it that doesn't change the physics.
Mm-hmm. And in this case, that operation is a reflection.
A reflection.
Yeah. Imagine a plane, an invisible plane, sitting exactly halfway between the two protons. You just reflect the whole system across that plane. We call that the reflection operator, P.
And mathematically, this P operator, it's really just a swap, isn't it?
It's just a swap. If you apply P to state 1,
You get state 2.
you get state 2.
Yeah.
And P applied to state 2 gives you state 1.
Yeah.
It just flips their roles.
We can even write it as a simple little matrix that basically just has the instructions swap the top and bottom.
And that's it. That physical idea that flipping the system gives you an identical reality, that is the very beginning of understanding quantum symmetry.
Okay, so we move from that very specific two-state reflection, P, to a much more general idea. Any possible symmetry operation, let's call it Q.
Right. So what's the ultimate test for Q to be a true symmetry of the whole system?
It has to do with time, right? With how the system evolves.
Exactly. The system is symmetric with respect to Q if the state after you apply Q. So
Okay.
QPSI evolves in the exact same way as the original state,
Yeah.
2PI. The symmetry can't break down over time.
And here's where it gets, really interesting. The operator for the system's total energy, the Hamiltonian H hat. That's the thing that governs time evolution.
It's the engine of the system.
So for the symmetry to hold true forever, there must be a mathematical requirement between Q and H.
There is. They must commute.
Okay, hold on. Commute. Let's break that down.
It just means the order doesn't matter. Applying the symmetry Q and then letting time evolve under H has to give you the exact same result as letting time evolve first and then applying the symmetry Q.
So QH equals HQ.
That's the condition.
That's the core takeaway right there. The universe's energy operator has to completely ignore the symmetry operation. If that handshake is true, that symmetry is locked in.
It's locked in. And if Q and H commute, something really profound happens in quantum mechanics. If you apply that symmetry operator Q to an energy state, the state itself can only change in one very specific, very limited way.
And that is?
It can only change by a phase factor. So Q times the psi equals e to the I alpha times Ci.
Let me just translate that. A phase factor, e to the I alpha, is basically a complex number with a length of 1. So why does this matter? Why isn't the state allowed to change more fundamentally?
Because the phase factor is like invisible to the real world. It's like spinning the state in place in a mathematical space. The physics, the probability of finding the particle somewhere.
The measurable stuff.
All the measurable stuff stays exactly the same. So finding an operator that commutes with the Hamiltonian is the same as finding a quantity that is conserved.
And that idea that the result is so restricted leads us straight to maybe the most famous restricted symmetry of them all, parity, or spatial inversion.
Right. We go from that simple two-state reflection to a much bigger idea, the general inversion operator, also usually called P.
So this is reflecting the entire universe through the origin. Every point x, y, z gets sent to its exact opposite. Minus x, minus y, minus z.
You're flipping everything. Left becomes right, up becomes down.
Front becomes back. It's like looking at the world in a mirror and then turning the mirror upside down.
Exactly. Now here's the critical feature. If you invert the system once, and then you do it
And
again,
I have to get back to where you started.
you must. P squared has to equal 1, the identity.
So if applying p once gives you that phase factor, e to the I alpha, applying it twice gives you e to the I alpha squared, and that has to equal 1.
Which is a huge restriction. It means that original phase factor, e to the I alpha, only has 2 possible values.
Plus 1 or minus 1.
That's it. And that's how we define parity as a quantum number.
So if you apply the inversion operator to a state, and you get back the exact same state with a plus 1.
We say that state has even parity. It's perfectly mirror symmetric.
And if you get back the state, but with a minus sign in front of
It
it,
has odd parity. And if the underlying physics, the Hamiltonian, is symmetric under inversion, then parity is conserved as a fixed, fundamental property of the system.
which for a long time everyone just assumed was true for, well, for everything.
For all of nature, yeah.
Okay, so we've got the rules. Now let's connect them to the big conservation laws we all learned in high school, the big 3: momentum, energy, and angular momentum.
This is the real genius of it, showing how these classical laws are just consequences of deep geometrical ideas. Let's start with position.
Okay, so if we take a whole experiment and we just move it 3 feet to the left, the physics shouldn't change.
The physics shouldn't change. That's symmetry under displacement or translation symmetry. We have an operator, d sub x, that shifts everything by some distance.
And if d sub x is a symmetry, it has to commute with the Hamiltonian.
And when it does, the quantity that gets conserved is the total momentum in the x direction. So conservation of momentum is a direct consequence of space being the same everywhere.
Wow. Okay, so momentum is conserved just because the location of the lab doesn't matter. What about time?
Same logic. If you run an experiment at noon, and then you run the exact same experiment at 1 o'clock,
Your results should be identical.
they should. That's time symmetry.
Oh.
If the physics doesn't change when you use a time delay operator, then the system's total energy, E, is conserved.
So energy is conserved because the laws of physics don't change over time.
The homogeneity of time guarantees it.
Amazing. Okay, and finally, rotation. This one always felt the trickiest.
It's a bit more complex, but the principle is the same. If a system is symmetric when you rotate it by some angle phi around, say, the z-axis,
The physics looks the same.
then the z component of angular momentum, j sub z, is conserved, and the relationship is precise. A rotation just changes the state by a phase factor that depends on the angular momentum.
So there it is, a complete structure. Homogeneous space gives you momentum conservation, homogeneous time gives you energy conservation, and isotropic space. Space looking the same in all directions gives you angular momentum conservation.
They aren't arbitrary rules. They are unavoidable consequences of the geometry of our universe.
And we can actually see this stuff in action. Feynman's example with polarized light is perfect.
It really is.
Right-hand circularly polarized light, RHC, carries a little packet of angular momentum plus h bar.
And left-hand circularly polarized light carries minus h bar. You can literally measure this tiny twist, this momentum.
All because of rotational symmetry, but this beautiful, perfect picture of universal symmetry, it hit a huge roadblock.
A massive one in the 1950s. Which brings us to the most critical experiment in this whole story. The decay of the lambda zero particle.
Okay, so the lambda zero, it's a particle, it doesn't live very long, it decays into a proton and a negative pion.
Correct, and the angular momentum has to be conserved. It's a rock-solid law. So if the lambda starts with a spin of 1/2 pointing up, the proton and pion have to fly off in a way that balances that initial spin.
Meaning the proton spin has to end up pointing either up or down relative to its direction of motion.
Right, now here's the thing. At the time, it was an article of faith that parity was also conserved. Always.
The mirror image symmetry.
Yes. And if parity were conserved here, the decay should be perfectly symmetric. The probability of the proton spinning up should be exactly equal to the probability of it spinning down.
The mirror image of the decay should be just as likely, but that's not what they found, is it?
Not at all. The experiment showed the decay was strongly asymmetric. There was a clear, measurable preference for the proton to spin one way over the other.
Wait, so the mirror image of the decay is different, is a different physical process. That's wild.
It was a shockwave. It meant that the weak force, which governs this decay, does not respect parity symmetry. The mathematical manual for the weak force does not commute with the parity operator, P.
The symmetry is broken.
It's broken. If you watch the lambda zero decay in a mirror, you are seeing a process that doesn't happen with the same probability in the real world. A fundamental law of physics can tell left from right.
That's incredible. So what's the final takeaway from this whole chapter?
I think it's that the most reliable bedrock laws we have, conservation of momentum, energy, angular momentum, they come directly from the simple geometric symmetries of space and time.
When an operation commutes with the Hamiltonian, you get a conservation law. It's a beautiful connection.
It is. But then you have this crucial twist, this nuance that quantum mechanics revealed.
The violation of parity.
Exactly. It proves that not all fundamental laws of nature are perfectly symmetric under mirror reflection. Sometimes the key to understanding the universe isn't just finding a symmetry.
It's finding where the symmetry breaks.
That's where you find new physics.
We hope you enjoyed this deep dive into symmetry and the foundations of conservation. Thank you for listening.